like sunshine, like springtime, like something's in the water and I'm taking a deep dive. I'm feeling so weightless, like I'm gonna make it, and nothing in the universe can take this. I can see it clearly now, nothing gonna bring me down. I got my head held high, I'm on my way, and I'm following the signs to my happy place. I'm walking in the light of a brand new day, and I'm right where I belong, in my happy place. I got my head held high, I'm on my way, and I'm following the signs to my happy place. I'm walking in the light of a brand new day, and I'm right where I belong, in my happy place. And I'm right where I belong, in my happy place. And I'm right where I belong, in my happy place.
Welcome to the National University of Singapore, Yonglulin School of Medicine's Healthy Longevity webinar. It's great to be here. I'm coming to you from France today, so it's a nice day here in France. And I took some time out, though, to bring on Emil Kendziorra, who will be with us tonight. And I think it's going to be an interesting show because a lot of you have said to us that you want to hear some of the other kinds of research and thought that's going into longevity medicine these days. And so I wanted to bring Emil on to talk about biostasis. So he'll be doing that in a few minutes. Before we get to that, though, I'd like to remind you to use the Q&A function. I'm sure there'll be a lot of questions for tonight's show. And I want to introduce Shailesh Nathan, who's an intern at Temasek Polytech, and he'll be talking about his project.
Hi everyone, as mentioned, my name is Shailesh and today I'll be talking about my project. This project is about finding the best out of two methods, submit and FICL, for isolating a specific group of cells known as peripheral blood mononuclear cells, PBMCs, from whole blood. Starting off, what are these cells? These are one of the first few cells to respond to protect the body against infection and diseases. They also remove cancer cells and allow us to study immunology from outside the body. So overall, PBMCs play a vital role in the immune system of the body. I would like to introduce a process known as centrifugation. This is the main step in both isolation methods. Centrifugation is basically spinning a tube filled with a liquid suspension to segregate the solid particles at the bottom. It will then be easier to obtain just the liquid, which is the supernatant, by pouring it carefully into another test tube, or just the solid, which is the precipitate, by pouring away and discarding the liquid. The type of centrifugation used in this project is known as density gradient centrifugation. This process divides particles in a fluid into separate fractions according to their density. Low density particles accumulate at the bottom, followed by the higher density particles in an increasing order. However, for this type of centrifugation, apart from the fluid that needs to be divided, density gradient medium is also added to aid the division of the fluid into different fractions. Here's the first method for isolation, using submit tubes. This is a special tube manufactured by Stem Cell Technologies, which contains an insert. We add a density gradient medium called lymphoprep inside the insert and layer the blood on top of it before centrifuging the tube. So if you look at the figure on the top left, it's a simplified diagram on how centrifugation separates the blood fractions. And the picture on bottom left shows the blood fractions in real life. Advantages of this method include a shorter time for the whole process to be completed while giving a higher throughput, prevention of contamination by the red blood cells, and minimizing chances of human error. However, one drawback is that there is a slightly lower cell count when compared to FICL, which I will be talking about next. As for FICL, a normal 50 ml tube will be used. FICL packed density gradient medium will be added to the bottom of the tube in the ratio of 1:2 to blood. Once blood is layered on top of the FICL, the tube will be then centrifuged. The two images on the left show the separated blood fractions after centrifugation. The mononuclear cell layer, where PBMCs can be found, is clearer on the animated picture. Advantages of this method is that there will be higher cell count compared to the previous method, and there are lesser steps. However, the time this process takes to be completed is around 1.5 to 2 hours. There is also a higher chance of the operator making mistakes due to harder techniques, and results may vary between each operator as well. Overall, the aims of this project is to optimize a protocol that allows effective isolation of PBMCs, which means we have better recovery of these cells from the blood. We also want to reduce contamination of PBMCs, and most importantly, ensure that the standard operating procedure is simple and reliable enough to allow any user to be trained. That's all from my presentation. Thank you.
Thank you. So much of what we do is dependent on having the best techniques and technology, and especially trying to isolate things from blood. Most of the analysis of biomarkers of aging come from analysis of blood, and we have to be able to get as many cells as possible from limited amounts of blood supply. So this kind of research will help us do our job better and get better results. I want to turn now to Emil Kendziorra, who has a doctorate degree in medicine from University Medical Center in Göttingen. He's the president of the board and a trustee of the European Biostasis Foundation based in Switzerland, and CEO of Tomorrow Biostasis based in Germany. But before that, he also had a very strong background in medicine and cancer research and in entrepreneurship. He's been CEO of multiple tech companies and medical companies, and most recently as a founder and CEO of MedLanes and Feedback. And so today he's going to be talking about something that I think is a different approach to longevity, and it's more based on the idea of not just extending your lifespan and health span by a few years, but having more dramatic effects. And this is one way to potentially get there. So he's going to tell you about an introduction to medical biostasis. Thanks for coming on the show, Emil.
Brian, thanks a lot for the kind introduction. Yeah, I'm getting right into it. All right. So as Brian just said, the talk today will be about medical biostasis. So since the introduction has already been done, just really briefly to give you a bit of background, right? So basically, I come from the longevity field. So my original plan was to, do a postdoc in that field. And then after studying medicine with a very strong focus on always doing research, seeing the least possible amount of patients and spending the most possible amount of time in the lab. But then I got more and more, in quotation marks, sidetracked doing tech companies. And then in the end, decided to take these medical biostasis approach to the idea of how to live potentially significantly longer, right? So I'll give you a bit of introduction about how the field currently progresses, what state of the art in science, and then how this plays into the field of longevity. And then, of course, I'm more than happy to answer any question. So I think when we talk about this topic, because it's arguably slightly further maybe on the edge of the Overton window than what is health span extension right now, I think it's always very important to remember that in any type of research and any type of technical innovation, what might have seemed impossible in the past, or what might even seem impossible right now, is then relatively quickly with technological advancement, it might be possible tomorrow. And of course, here my example, because I'm giving these talks to doctors as well, is a picture of the first heart transplantation, right? So, if you would have asked a doctor 20 years or 30 years or even maybe 10 years before the first heart transplantation, then a lot of doctors would probably have said, hey, listen, either this is not possible at all, or we shouldn't even think about it. This seems kind of, in quotation marks, a bit weird, taking a heart from one patient and transplanting it to another. But of course, now it's a procedure that no one would ever want to miss, right? And it's absolutely, in quotation marks, standard. So, what used to be impossible then kind of moves into the realm of possibility. And of course, after it becomes possible, in some cases, it becomes absolute standard and not something that people think about much anymore. So I think when we talk about topics like medical biostasis and these kinds of things, then I think it's always good to keep in the back of your head that technological advancement works like that in usual. It doesn't even need to be medical. It can be taking a plane to fly to another continent, right? Which also, if you just go a bit further back, was absolutely unimaginable to basically everybody. And now it's absolutely, standard procedure. But this is just as a kind of a bit of a background, right? So what is biostasis, or how it is sometimes called cryopreservation, right? So basically, fundamentally, it's something that a lot of people do every day in a lab, right? You use very low temperatures and specialized cryoprotective agents, for example, DMSO, right, to cool down cells or other tissues or even organs or even organisms without damaging the material, right, without ice formation and so on. And then you can basically keep that, let's say, in most cases, of course, most of you might have done that, cells in this cryopreservation, right, until you need them again. You can do that right now with certain tissues. You can do that with some organs, even though relatively small organs. And last but not least, you can do it with some organisms. The goal, of course, here would be, right, that you can store this biological material, you can preserve this biological material for very, very long durations, practically or technically indefinite durations, without accumulating any damage during that time. And as I just said, so today it is possible to do cells, you can do tissues, you can do small organs, not human organs, but animal organs. You can even do some organisms. For example, C. elegans is very easy or relatively easy to cryopreserve. And what's not possible yet is to do cryopreservation with human organs, at least not with whole organs. It's not possible to cryopreserve mammals yet. And it is also not possible yet to cryopreserve whole humans. And of course, when we talk about longevity, as you might have guessed, what I'm working on is on researching how to cryopreserve whole humans. And of course, as we will discuss in the end, this is not something where you could just choose to be cryopreserved, but it's basically only done if any other medical intervention has failed to cure the person. All right. What's important to note, right? So here on the left, you see one of the pictures. If we talk about biostasis or human cryopreservation, it's one of the pictures that if I give interviews to some articles, this is always kind of the visual kind of representation that they use, right? And of course, it's very important to remember that this ice cube is exactly the opposite of what we want to do, right? So everything we do, a lot of what we do, is to not freeze anything, because freezing, of course, means having ice crystals form, and ice crystals is as everybody probably knows, they're sharp, so that they destroy tissue, right? So a lot of what we do is to reach a state which is called a vitrified state, which is basically an amorphous glass-like state where you can cool things down to very, very low temperatures. In most cases, -140 to -196. So either in liquid nitrogen or in the gas phase above liquid nitrogen, to then have this vitrified state where no ice crystals have formed, where you can then reach this cryopreserved state, right? Yeah, and as I said, you can do this with a range of things, and you can maintain that condition practically indefinite without any metabolic activity at these temperatures. Of course, there is no metabolic activity. There is no degradation happening at all. I briefly said that you can do that with a couple of things, and just to give you a bit of a better understanding what is currently possible, I would briefly introduce 3 landmark papers that have been published over the last few years, showing kind of what is currently done. Here on the left, you kind of see 2 kidneys, right? One very clearly, the left one very clearly frozen, a lot of damage, a lot of ice crystals, no viability if you take that kidney out of cryopreservation. And then on the right side, a vitrified kidney, which of course looks much healthier and can actually be taken out of cryopreservation, warmed up again, and then retransplanted, in this case, into a rabbit. And then the kidney works, the rabbit continues to live on with that kidney that was in cryostasis before. And of course, that paper is from Greg Fay at 21st CM in the US, one of the leading cryobiologists and one of the most preeminent researchers in that field. So with organs, you can use that technology, right? Then when we talk about C. elegans is cryopreservable, right? You can take it into cryopreservation and you can bring it back from these negative 196 temperatures, and basically it continues to live on. And not only that, it was shown in this 2015 paper that in fact the memory, and of course memory in C. elegans needs to be, I guess, in quotation marks, the memory, which is basically in aversion to a chemical, is being maintained, right? And of course, if we talk about human cryopreservation, or if we go on to that, then of course it only makes sense as a longevity technique if memory is being maintained, right? And then last but not least, now, of course, some might argue, well, you know, that's all great, but the brain is a different beast. In 2015, by Robert McIntyre and also at the lab of Greg Fay, they showed with a slightly alternative version to cryopreservation, which is called aldehyde stabilized cryopreservation, which is combining cryopreservation with a chemical fixative, that you can preserve neural tissue without there being any obvious differences. So with very clear neural structures being clearly identifiable, right? And then of course these points kind of all need to come together. And as I said, this is a relatively early research field, right? Meaning there's still a lot of open problems, right? So everything I said so far, one of the main reasons why cryopreservation works in certain cases and doesn't work in other cases is, by and large, making cryopreservation work in larger organs or even whole humans or organisms. It's almost a physics problem. It's almost not a biology problem. It's almost physics, due to the fact that you need to be able to warm and cool large volumes very fast. And just physically, just due to, you know, basically thermodynamics, it's very difficult to cool large volumes and also warm up large volumes very fast. You can do the cooling part. The cooling part is significantly easier to do. The warming part is actually the difficult part. And of course, if anybody has questions about this, I'm more than happy to elaborate on that. Then these cryoprotective agents are toxic. For those of you who work in a lab, you know, you don't put your cells into DMSO and then let them stand at room temperature for a long time, right? You cool them down as quick as possible due to these cryoprotective agents being toxic, especially at high temperatures. There's a lot of ischemic damage, or we do everything to reduce the ischemic damage as much as possible during the cooling procedure, or prior to that. There is a good amount of ischemic damage that needs to be solved. There's still some amount of ice nucleation and even ice crystal growth. And last but not least, if you cool large volumes down, especially below the glass transition temperature, that is that temperature where basically the tissue goes into this glass-like amorphous state. And of course, glass-like amorphous state sounds like a bit of a tongue twister. It's a state where the tissue is basically a solid like a glass, right? And now if you cool down a large volume that is kind of a solid, right? And you unfortunately, due to how you do the cooling, you cool it at different rates, like different parts cool down at different rates, which generates thermal stress in that tissue, which can lead to damage. So all in all, there's a lot still needs to be done, but a couple of things, kind of a proof of principle, a proof of concept, is already possible. Now, the big question here, of course, is, well, why should anybody who might be interested in longevity be interested in cryopreservation or in biostasis? And practically, very simply, this graph, a lot of you might be aware of, right? It's basically the mobility compression graph. And of course, this one only goes till 1980, but there's another one that goes further, right? So all of these curves basically show, well, we're getting better and better, and have actually been getting better for quite a bit of time to make or reduce morbidity, right? Squaring of the mobility curve, mobility compression, or however you want to call it. But if you look into the red circle, what we definitely have not been making any significant progress on is on increasing average life expectancy, right? Average or maximum life expectancy, right? And average life expectancy, of course, over the last decades or even centuries has mostly gone up due to child mortality going down, and then some amount of better hygiene and so on. So by and large, the approach that this medical biostasis and cryopreservation topic is taking is that we're not really working on health span expansion, right? And while health span expansion in my mind is absolutely important, it's absolutely important that the morbidity curve gets more compressed so that people who are in their last, let's say, third or fourth of their life have good quality of life, have good mental fitness, physical fitness, and so on. In my mind, I'm interested in both, right? And of course, everybody who works at our research institute is arguably interested in both, right? They would like to live healthy, but they would also like to have the chance to live long, right? And when I say long, I include longer, right? And of course, this is very much everybody's personal choice if they're interested in that. But the idea here would be that if medical technology doesn't progress fast enough, then something like human cryopreservation, where you could preserve a body with the least possible amount of damage, might be a way where then future technology might be able to fix these problems that currently cannot be fixed. So to summarize that point, or to say it in a different way, extending maximum lifespan seems to be much, much harder than extending health span. Partly, of course, also due to the fact that expanding health span is significantly more kind of generally, or getting more generally accepted in a larger part of the population, whereas expanding maximum lifespan is still kind of a discussion that is being had if this is something that makes sense to go for, right? But to be fair, so I'm a doctor by training, and unfortunately, there's a lot of cases where the only thing that the doctors can tell the patient is that, and my background is cancer research, right? So there's a lot of cases where the only thing that you can tell the patient is that, well, we can take the pain away, but we will not be able to cure the patient, right? The patient will die, right? And in my mind, that's a pretty unacceptable situation. So the vision behind cryopreservation is, and I must very much stress, it's just a chance, right? The vision behind it is that if there are currently incurable conditions, incurable diseases, right, where the patient, whatever we do with all of our medical technology and capabilities that we have, if all things have been tried and still we just don't have the technology or the knowledge yet to cure certain diseases, then as a last line of defense effort, as a last ditch effort, cryopreservation of the whole human might be a way where these people remain or maintain a chance of having that disease cured in the future, because a lot of diseases that are currently, that are not cured right now, will probably be cured in the future. And of course, once all these problems and technological topics that I discussed before are solved, then it is potentially possible to resuscitate that human, cure the disease that has led to the patient's death, and then have the patient live on. And again, so why would anybody want to do that, right? And so I think there's a couple of things, like a couple of fundamental arguments why I think in principle this is something that makes sense, right? So in my mind, morally, I think how long people should live should pretty much be an individual choice, right? And of course, some people might disagree here, and that's totally fine. But for everybody who would like to kind of have a self-determined lifespan, currently, of course, medically, that's not possible yet. And then again, very important to state this is an absolute last resort option, right? Only if all the other medical, treatments, everything that you can do with our current technology have been exhausted, and there's no other option that we have, then this might make sense, right? Similar to where this, you have this idea in medicine that if everything has been tried, that then patient and doctor can together decide to go for for unproven treatments, like, for example, in compassionate use cases and so on. Because the alternative, and this I think is the core argument here, the alternative is unrecoverable death, right? In every cryopreservation case, you only ever do this after the patient has been legally pronounced. And of course, now, medically speaking, there's very little difference between, 1 second, 10 seconds, or even a minute before circulatory arrest and a minute after circulatory arrest, right? Of course, circulatory arrest is not sufficient. It would also be the legal pronouncement, right, which works different in different countries. But usually it's somehow correlated to circulatory arrest. Now, the idea would be that you would preserve the patient at a time when the body is still technically possible to maintain life, right? Even though there might be a disease that currently makes it not possible to maintain that, and then wait until in the future it might be fixable, right? Until that time, basically to bridge the time until medical technology has advanced enough. Again, it's very important to state, right? This is just a chance, and no one, neither me nor anybody else, can tell you how high this chance is. It might be very, very low, right? But then again, that's why, my institute is doing research in that space, because I would argue that the alternative in these cases is worse, right? Because the alternative would be, in most countries, it's either cremation or burial, where any chance to maintain, to be woken up in the future is zero. Important. Informed consent, really, really important. People need to, if they should choose to do that, they should. It's absolutely crucial that they understand that it's an unknown probability. It might be a very low probability, and so on. A lot of downsides. There's tremendous amounts of additional research needed, and it's relatively expensive right now. So it should be significantly more affordable. It's one of the things that we do, working on that. And very briefly, showing you a couple of pictures. So this is my research institute that is run by a nonprofit research foundation in Switzerland, kind of a combination of a wet lab and then also imaging like CT scanners, medical facility, and so on and so on, and also cryostasis or cryo liquid nitrogen long-term storage in very large amounts. Then I'm running basically a medical company in Germany, or based in Germany, that covers, if people want to sign up, they can do that. We have medical teams and so on who do the procedures. If anybody's interested in that topic in general, we run an annual conference in Zurich in Switzerland. The next one will be in the end of October in 2023. Always a very nice conference where everybody internationally from that space comes to Zurich and basically has a scientific symposium. And we're starting more and more also to fund. We are a cryo-DAO kind of system. We fund basic research in that space, just to be able to do something to change all these problems that I mentioned in the past. Right. So lastly, if anybody's interested, I'm more than happy to talk about this topic, to dig deeper. So feel free to reach out. And now, without further ado, I'm more than happy to answer any question that there might be.
So thanks, Emil. I think that was a great overview of the situation. I've heard people talk about this for a long time. And what I really appreciate about your presentations is you're very realistic and transparent about where we are and what the possibilities are. So that's great. Maybe I could start by, there's two phases to this, right? To put it sort of bluntly, there's freezing and thawing.
Sure.
And it sounds like you feel like we're closer in terms of the preservation state than the revival state. And Maybe you can estimate sort of, you mentioned some of the current needs of research problems to solve, but maybe on more practical terms, what do you think the chances of solving each of those are, and what's the time frame?
Yeah, so now we move away from any, from we reduce the scientific rigor and move into kind of. So the reason why I'm being so careful with this statement, because I mean, like, this is a question, of course, that every journalist is always asking, right? So when does this work? Like, how far away are we? The problem is, it really moves into speculation territory. And the reason for that is that, humans are pretty good at predicting things or estimating things when it's kind of linear, when there's kind of a linear curve that kind of goes up and you kind of see, you can do a linear prediction. The problem here is there's a range of almost like basic science fundamental breakthroughs needed, like step function kind of stuff, to make this work, right? So and the second reason for why I feel like it's very hard to predict it is because you would always, if you would need to predict it based on current amounts of funding, then it would be kind of like, so it depends, of course, of the amount of funding, and the amount of funding in that space currently, it's very limited. So if we would use current amounts of funding, then I would put it at a time when basically all predictions break apart, 50 years plus. Right? Not because I think it's really 50 years, but because I feel like between 50 and more years, any prediction is almost worth it. It's like, rolling a dice. I'm not aware of anything where I would say it's fundamentally not possible. So again, you can do it with organs, right? We know why we can't do it with larger organs. We know why we can't do it with whole humans. At least we know range of reasons. So I would say so. Like potentially reviving a mammal might be a couple of decades, right? A rat, a mouse, right? Maybe, I don't think it's 10. I would say it's like 20, 30, 40, somewhere in that range, right? And then humans is 50 years plus. And for me, making a prediction 50 years, I might as well say 100, right? So there's very little difference between these two numbers. Yeah.
So resources would accelerate that, I think you would speculate, right?
Yeah, so there's a couple of advantages. Usually, if it's not a biology problem, the complexity space of a physics problem is usually smaller. There's more, you can test it easy, right? So like we don't need to test stuff. So if you want to test a new drug, you basically need to test it in humans, right? The complexity is so big that you need to test it in a real life situation, right? Which of course makes everything very difficult. A lot of safety, safety guidelines required, and so on and so on. Whereas in cryopreservation, if you could warm up a large organ, then the jump from that to being able to do a human is probably, and again, it's a bit speculative, of course, it's probably less because it's mostly physics. And physics, usually the data is more transferable between, let's say, a rat to a human, whereas in biology, this is a big jump, right? Yeah. So funding would just help to run through more of these experiments and do more.
So is there a lot of work going on right now trying to do this in mammals? I mean, I'm not aware of the breadth of the field, like say in mice or even simpler.
Little. And the reason for that is we're talking about probably middle double digits of millions in funding per year here, right? Which of course is less than any single research, any cancer company has more than that per year, basically, right? Mm-hmm. So we're talking really about small amounts right now. There is work in rats going on, right? But again, like kind of mostly still most of the research currently is on the making sure that you can do better cryopreservations, right? And then using neural ultrastructure to check if the cryopreservation was done well. And then there's some research how to rewarming, but it's almost basic science. So for example, there's a research project that we're currently considering funding where they use a specific type of, or like a specific arrangement of thousands of ultrasound transducers that are inside an MRI, where the MRI is basically guiding or in real time basically like adapting the ultrasonic transducers to do uniform warming, right? With very, very fast warming rates, so hundreds of degrees per minute delta. But it's basic science.
And I think it's intriguing though that the worm can be, brought back and then it retains long-term memories. I know that we're talking about 300 and something neurons in a worm, but
Sure.
One of the concerns has always been that, after a person dies, depending on time, the neural connections are going to degrade, and the brain is going to change very quickly. And maybe that's over. Maybe there's more concern there than there should be. What is the stability of the brain after someone is pronounced dead?
Yeah, so the stability is basically a function of time and temperature, right? There's a saying in medicine that says you're only dead when you're warm and dead, right? And the logic here is that basically what happens, right? If the heart stops beating and the brain is not supplied with oxygen anymore, then cells start different types of degradation processes, right? And they're energy dependent, right? So at least in the beginning, right? So if you reduce, and they do this because they don't have enough energy anymore, right? There's not enough oxygen. So if you reduce metabolic rate, and of course cooling reduces metabolic rate, then the cell has more time to not trigger these degradation processes. And if these degradation processes are triggered, then they're still, again, initially metabolic, that they're dependent on active metabolism, right? So if you cool down faster now, the cell can't execute this shutdown process, right? So if you die at room temperature, or more precisely, if your heart stops beating at room temperature, you have maybe 5-6 minutes until you need to be resuscitated. Otherwise, there's currently, with current technology, irrecoverable brain damage. But there have been cases where people, usually one of the common cases is where children, if they go ice skiing on some lake in winter, and then they fall into the water, and there's one of the famous cases is a doctor who died, or the heart stopped beating in a skiing accident, and she was like an hour plus without a heartbeat, and then made a full recovery due to the temperature, right? And in principle, this is the same idea here. You cool down, and due to that, you have less neural damage. But I don't want to make this sound too simple, right? So the fact that C. elegans works is due to the size of C. elegans. You can cool down C. elegans very, very fast. You can warm up C. elegans very, very fast, right? So it sounds like, hey, if it works there, shouldn't it work soon also in humans? No, there's a tremendous difference in complexity due to humans being significantly larger.
Yeah, there was a lot of excitement several years ago, and it's continued to some extent, on hydrogen sulfide as a means of slowing down metabolism, and it may assist in surgery, it may assist in all kinds of things. I wonder if there's some sort of overlap between H2S and cryopreservation. Are those two things compatible together, or would they be
compatible?
Beneficial?
Yeah, probably. I'm not aware of any research that combines these two things, right? Because if you put someone on bypass after they've died, right, and then cool down internally, you can cool down pretty fast, right? Combine liquid ventilation with bypass, you can cool down pretty fast. In most cases, of course, due to this being kind of a very experimental procedure, right, you cannot do anything before pronouncement, right? So yeah, so I'm not aware of any research that looks at these two things together.
Yeah. Again, I think that more resources to look at this. I mean, it's a fundamentally interesting biologic problem, almost independently of your views on whether it should be done or not for yourself or someone.
Oh yeah, absolutely, absolutely.
It's a really interesting area that I think will lead to a lot of technological breakthroughs. You mentioned something about the foundation, and then there's a company also. So, what is the public interest in this so far? I mean, how many people are aware of this? What is their interest related to that?
Yeah, so interest actually surprised us a lot. So the first thing we did, just to answer that question, because no one really knows, right? This is a very small field. It's not like there's been a lot of consultants doing large studies. We ran a large study in Germany and in the US. It's actually published if anybody wants to look it up. Gillette et al. In PLS1. Basically a comprehensive overview about what is the sentiment towards this topic, right? With around, I think, a couple thousand people who answered that survey, asking them, hey, is cryopreservation something you might consider as one of your end-of-life choices? And then dependent on if it's Germany is like, 22% of population says this is something I might consider. In the US, it's a bit higher. It's more 30%. In the US, to be fair, there's a small bias in our data because we recruited online. So we have an overrepresentation of overrepresentation of urban people, people living in urban population centers and so on. But still, the interest is tremendous. 30% say, this is something I consider. Then we didn't believe this initially, so we made the question like more strict. So we asked like, would you want to talk to a company that offers that tomorrow? And do you want to give us your email address? Right at that point, it was out of the published data; it was just for our own data. And then we went down to 17%. 17% of people gave their email address to be. We didn't contact them, but so. It seems to be that there's a couple other studies by other groups who've done that. It's always between 20 to 30% of population says this is something I'm interested in. Doesn't mean these people sign up, right? Interest doesn't mean intent. Intent doesn't mean I'm doing it tomorrow. So we now, like on the company side, we've been around for a year or so. We have we're working towards getting to 1,000 people now fully signed up, which of course is also due to the fact that the price point for it is currently, unfortunately, around 200,000 euros, right? So it's kind of prohibitively expensive for a good amount of people, and we're working on making that significantly more affordable.
For the people that said they weren't interested, did you ask why? Was it because they thought it was just not going to be possible, or because they thought it shouldn't be done, or what were their reasons?
Yeah, so it's a combination of things, right? So some people think it's not possible. I don't think this, if I remember correctly, this is not the largest group. The largest group, I mean, again, it's a large minority, 30%, but the majority still needs to wrap their head around it, right? Some people are. I think the biggest problem seems to be that people have not engaged with this topic yet and have not for themselves thought about it. Is this something I want to do or not? Mm-hmm. Right. And of course, kind of from a kind of, quick reaction kind of answer, it would be, no, why would I want to do this? Right. I'm pretty sure that most people would reconsider if they would be in relatively good health, but still diagnosed, even if it's at 85 with a terminal disease. I think at that point, most people who haven't gone through a long time of suffering period, right, would say, well, listen, a year more, sure, why not, right? I would definitely prefer that. So I think it's mostly an engagement with the topic. It's a topic that, apart from sci-fi or some science fiction movies, most people have not actively thought about as if this is something that they could really do or could really choose. And then, of course, there's a list of people who say, hey, listen, I'm totally fine with being with dying tomorrow, right? So I've done everything in my life, from a philosophical standpoint. I don't see any value in that. And that's, of course, also fine. If people,
there's economics of scale, right? So it's 200,000 euro now. I mean, right now I'm in Europe, and the value of the euro keeps going down. So I guess it's getting cheaper.
Sure.
So.
It's actually more expensive now in Europe. No, it's not. But sure.
For outsiders in Singapore.
Yeah, exactly.
Yeah. I think though that what do you think a limit could be if you had scale? I mean, how expensive? What can the price come down to?
So the good thing for cryopreservation is that everything goes down with scale tremendously. So what makes it currently expensive? The doctors. So just the doctors who need to stand around for a long time and there's not many cases, right? Then literally the place where cryopreserved people are being kept, for example, here in Switzerland, and the cost of liquid nitrogen. The cost of liquid nitrogen at scale goes down tremendously. So does the doctor's cost. So you would be able to offer it at a similar price to a large scale, like a large operation, right? Not US prices, Euro prices. So let's say, 10,000, 15,000, somewhere in that range. Everything is like the cost goes down. Luckily, all these points, like amount of space, like how large your facility is, goes down crazy with scale. Liquid nitrogen, if you have large volume tanks, you have a better ratio between surface where you lose liquid nitrogen and volume. And last but not least, medical teams, as long as they're basically doing an operation every day, right, or multiple every day, then cost goes down significantly as well. So maybe, yeah.
Sorry, go ahead.
Yeah, long term. So our first goal is to bring it down to 50K. Then I think 25 can be reached relatively simple. And then if you want to bring it down to 12 or 10, that makes it a bit harder. At that point, you really need scale. That's not going to be that quick, but 25 is already significantly better than 200.
Just maybe one more thought and question. There's
Sure.
Another controversial topic is sort of assisted suicide, or people choosing when they want to die. And especially in the context of someone has a terminal condition, and then the doctors are encourage them to try every last thing, and then the last 3 months of their life they're miserable. It would seem like that would also interface with this, right? It would probably not be advisable, if you plan to get rejuvenated at some point later, to wait until the last possible minute. And so I wonder how people think about those two things together.
So on a medical standpoint, I agree with you, right? So let's say you have a neurodegenerative disease, right? Then probably you don't want to wait until the last minute, right? On the other hand, it's a very difficult ethical discussion. So we have decided to, until there's more ethical thought about it and more concepts and more guidelines, we don't combine these two topics at all. They're fully separated. You can, of course, go to any organization, say there's organizations in Switzerland and Netherlands, also in the US with Death with Dignity and so on, right? Where you can go and say, listen, I want to do certain types of physician-assisted suicide, whatever is legal in that country. We don't get involved in that part at all. Then once you're pronounced, of course, you can be cryopreserved after. But these two things don't mix, right? Because also the people who advocate for death with dignity and so on, they don't want to mix it, because also it's a contentious topic on their side. And combining it with another potentially contentious topic is probably not good for either side. So clear separation, but technically you can do them sequentially.
Yeah. Interesting. Maybe what we'll do is bring Xiaoping in. Xiaoping's become a regular on the show now. I don't know, that's there may be 6 or 7 of these you've done now. So he's going to collate questions from the audience, and we have a lot of questions. So Xiaoping.
Okay, thank you so much, Brian. Dr. Kendziorra, thank you for your talk. That was a really cool talk. And you know what? A lot of people are really interested even in Tomorrow Biostasis. So I start with the first question that is most upvoted. So David would like to know, how would Tomorrow Biostasis remain financially stable to ensure customer under cryopreservation remain cryopreserved if the company undergoes bankruptcy or something like that?
Yes, very, very important topic. So the most important part here being that Tomorrow Biostasis does not maintain cryopreservation in itself. We are kind of the service company. We're the medical company, right? We have the doctors and we do the procedure and so on. And then once the person is cryopreserved, we hand them over to a non-profit foundation. Companies are horrible at being around for long times. And even if they're around for a long time, they start doing other stuff, right? So I would never want to be cryopreserved with a for-profit organization. Absolutely horrible idea in my mind. So we do the long-term storage at a non-profit foundation here in Switzerland, where the purpose of that foundation, the fact that they are there to maintain people in cryopreservation, is protected. There's like a government body that even if a future board of that foundation wants to change what this foundation does, they can't. And from a money perspective, now, since no one can say how long it might take until revival might be possible, you need to be able to maintain it indefinitely. So what we do, this is the main reason why it's so expensive. Around 120,000 of those 200,000 euros are being put aside and invested with around 1 to 2% above inflation. Historically, that always was possible. Currently, inflation is too high, of course, to maintain that, but arguably, probably inflation will go back to 2%. And then you only use the interest of that money, the return, to to pay for maintenance cost. So the principal amount always stays the same. In the end, I think that there's no perfect guarantee, but non-profit foundations and having basically only using interest, and there's a lot of different things like smaller topics we do that would be too long to explain now. This makes it pretty safe, at least in as much as I know.
Okay, thank you so much for that questions. Since we are talking about the financial aspect, Samla would like to know that she wonder if there could be any insurance willing to underwrite such a cryopreservation currently available.
Kind of. So we actually, most people who sign up with us actually fund their cryopreservation with insurance. So we have one large insurance partner. It's just one of them. You can use any insurance technically. Basically, what you can do, you can decide to take out life insurance, either term life insurance, which is relatively affordable but has an end date, or whole life insurance, which is basically a savings plan with an automated payout. So should you now at some point die, either during the coverage period or in whole life insurance, whenever, then that insurance pays out that amount of money that is required for cryopreservation. So you can actually do it. Most of the people who are signed up with us, they're somewhere between 30 to 40, and they pay around 50 euros a month, where partly that goes to the life insurance to then be covered by that. Yeah, so it is possible. Arguably, it's even advisable because no one should wire us 200,000 euros because we would need to hold that amount in truster accounts. So we can't invest it. And with any amount of inflation, even going down to 2%, if you have 2% inflation over, let's say, 40 years, a lot of your money is gone. So absolutely not advisable. Insurance makes a lot of sense in this case.
Okay, thank you. That is a very interesting point. People would like to consider about the alternative. So Anna actually asked that for those who can't wait for the research to advance, she would love to hear your thoughts on the available option that we have today, such as an Arizona-based alcohol company. What is the difference between Tomorrow Biostasis and alcohol?
Yeah, so there have been cryopreservation organizations for ages. So Alco just celebrated its 50th birthday, right? And they're good guys. Like they want to make it work, right? But without being too negative, this field has been around for a long time, and little has gotten better. So it's kind of like, there was a time before Uber or any of these app enabled, and taxis also kind of worked, right? But there's a bit of an advantage, I would at least say, in kind of how you do it in a new way. So we're here to make this topic more approachable to a larger audience, and very importantly, invest more in science. Like the last time that cryopreservation something really changed was around 20 years ago, right? Since then, of course, the stuff has changed, but there was not any fundamental advance in science for around 20 years, right? So fundamentally, I think we do kind of the same. There's some differences. We do what is called field cryopreservation. So we have teams that do most of the cryopreservation procedure at the patient's bedside, right? Directly once the hospital releases after pronouncement. So you arguably have a bit better quality, but by and large, I think that the main difference is kind of almost the mindset thing, that we're definitely not happy with the quality, and it needs to get much, much better. Whereas other organizations in some kinds, not so much alcohol, but others have kind of, they got a bit somewhere between content and complacent, I think.
I see. So most of the most upward questions is about the operation rather than the basic science. People
Sure.
want to know that how is the medical team get ready all the time? Like, is it only available in Europe or is it like worldwide?
Yeah, so our team is only available in Europe, exactly due to that, right? So the amount of people who do currently sign up for cryopreservation is not large enough to have like teams, let's say one in the US, one here and one everywhere, right? So what we do, we have professional medical teams, and then we have smaller trained kind of like similar to EMTs, right? Where there's a group of people who can do kind of the first aid kind of thing. So technically, we can cover larger regions if there's a good first response team on site, right? And we're currently considering that we're discussing that with some organizations even globally or in certain countries. The procedure otherwise works like that in very briefly. Initially, it's similar to CPR, even though, of course, we don't want to resuscitate, right? So it's chest compressions, everything that increases metabolic activity, chest compressions, oxygen, you give medication to supply the brain with the remaining amount of oxygen, right? Then you at the same time start cooling. Initially, you cool outside just with ice water being flown around the body, and either with liquid ventilation or with nasopharyngeal lavage. So basically using every surface on the body that you can. Once you've cooled down a bit, you put the patient on bypass. That can either done basically a heart-lung machine that can either be done with femoral cannulation or median stenotomy and then aortic cannulation. And once you've done that, you cool down internally as well using basically the circulatory system. And then once you've cooled down enough or a bit more, then you start replacing all the fluids in the body against a cryoprotective agent, basically a medical grade antifreeze solution. And once you've done that, then you can cool down to cryogenic temperatures. That cool down you do very, very, very slowly, around 100 hours, to be able to not have thermal stress. And if anybody's interested, I mean, I can talk more about this, of course, but in the interest of time.
Okay, thank you so much. So you essentially cool down the body. That is the current best practice, right? Is there any research ongoing on how to further preserve it ongoing at your institute, or you know of anyone doing it right now?
Yeah, so once you're at cryogenic temperatures, there isn't really anything to do, right? So once you have reached the final storage temperature, at that point, nothing happens anymore. I'm not aware of anything that you would be able to improve during that time. What you can improve, you don't technically want to store at negative 196. You want to store at negative 140. The reason for that is that at negative 140, you go through what is called the glass transition temperature, meaning at that point, if you remember what I said in the talk, you go through this glass-like amorphous state. Now, when you cool down further from that point, you don't get any advantages. You just get more thermal stress. So you don't want to have that thermal stress, because thermal stress can lead to what is called cracking, basically macroscopic fractures in the tissue. So you want to do that. So we have one research project that currently works on what is called an ITS door, intermediate temperature storage door, where the tissue and the organs and the whole bodies are not stored in liquid nitrogen, but in above liquid nitrogen in the gas phase. And then, of course, there's a lot of details to have less of a temperature gradient. But basically, it's a better storage temperature. At that temperature, once you've reached whatever the storage temperature is, there's practically nothing to improve that I'm aware of.
Mm-hmm. Yes, our lab, we also do cryopreservation every day.
Sure, yeah.
Yes, it's a real possibility that it can work in the future. We highly believe that. And for fun, another question, the 200,000 euro, that price tag that you just mentioned, is for how long the duration of the vitrification? Is it for as long as possible? There must be a limit, right? So the audience asks.
Yeah, there is no limit. So it's indefinite. And how you do that, right? I mentioned it briefly, right? Around 80,000 is being used for the procedures, for the doctors, like all the material and so on. 120,000 euros are given to that non-profit foundation. And that non-profit foundation now invests that 120,000 euros, with the goal of getting 1 to 2% above inflation in return per year. 1 to 2% for 120,000 euros is somewhere between 1,200 and 2,400 euros per year. You need around 1,000 euros to maintain one patient in cryostasis per year. So as long as you can assume that you get 1 to 2% above inflation, right, with what historically was always possible. So US Treasury bonds was 1.9% above inflation over the last 50 years, right? Of course, it's a zigzag, there's up and downs, right? Currently, it's very difficult to get 2% above inflation easily, right? At least without risk. But then there are better years again that make it up. So you can keep people indefinitely as long as you are able to get this 1 to 2%, and as long as, geopolitically, nothing goes horribly wrong. But historically,
that's a big statement, Emil.
in those times, it is. If you would have asked me a year ago, I would have said this is probably not a problem. In those times, yes. But I'm optimistic. Switzerland has a good track record here.
I better jump in because we're running out of time. Thanks, Shoping, and thanks a lot, Emil. We'll have you back on at some point if there are any updates and see what's going on. I want to remind the participants to use the chat function and choose the panelists and all attendees option to leave comments and feedback. Particularly, that's important for this show. We've taken a different approach today on this show and looked at some of the more futuristic aspects of longevity research. And if there are others we could talk about as well. So if you're interested in these topics, let us know and we'll try to schedule more shows related to that. Look for news for our center and the School of Medicine in the end credits. We have a Twitter account. We'd love to have you come to that. There's a QR code that will be at the end of the webinar you can use to look at the Twitter account. We have a website for the Center for Healthy Longevity. There's also a QR code for that. So please keep interacting with us. Our next show will be next week, November 17th. We'll go back to talk again a little bit about NAD and healthy longevity with Professor Reichelt Houtkoper from Amsterdam University Medical Center. I'll be with you next week to talk to him. And we want to leave you with something that is always exciting, hearing about seniors sharing their sex secrets. Thanks for joining the show.
Senior citizens are having sex now more than ever.
Not me. Not me. Good luck to them, man. More power to them.
Well, I'm going to be 80 this year, and I have a boyfriend who just turned 83, and I have to say our sex life is great.
What's your big move?
What do you mean big move? I'm not telling any secrets.
What's your secret?
A little vodka couldn't hurt.
What is our secret? Well, you're not going to get pregnant.
If you do get pregnant, are you worried you're going to have a 30-year-old? What advice would you give to seniors who aren't having sex?
You have to use it, and if you don't use it, you're going to lose it.
And you're using it.
Darn right I am. I just did it today.
You just did it today?
Yes.
And who's the lucky lady?
My wife.
God bless you.
Yeah.
What are some turn-ons?
My turn on? A smile.
I like affection, kissing him on the neck, holding hands.
I don't have many turn-offs.
That's what I'm talking about.
I don't like rough. Some people do. It's okay for them, but I like gentle, caring, loving. Even if they don't love me, they should be loving.
So some romance, not just a one-way ticket to Pound Town.
Yeah, I would say so. Yeah, but I mean, Pound Town is better than nothing.
I'm feeling like sunshine, like springtime, like something's in the water and I'm taking a deep dive. I'm feeling so weightless, like I'm gonna make it, and nothing in the universe can take this. I can see it clearly now, nothing gonna bring me down.